Good afternoon from the UK. Welcome to the 23rd Surface Ventures webinar. Before we go any further, can you please write where you're joining us from today in the chat box on the right-hand side. And while you do that, let me introduce myself. My name is Tahid Khan. I'm a Vice President at Surface Ventures and I'm your host for today. We are a non-for-profit organization and our mission is to really provide world-class surface engineering education for academia and industry. So every month, we aim to bring you a sector-leading speaker to present the current challenges and future trends in surface engineering, alongside surface engineering workshops and live equipment demonstration. Great, that seems to be working. Thank you. It seems we've got great many places there. So today, it's my pleasure to introduce Dr. Astrid Drechsler of Leibniz Institute of Polymer Research. Dr. Astrid studied physics at FSU Jena. After 2 years of working in the microelectronics industry, she went to TU Dresden and received her PhD degree in the field of physical chemistry. In 1997, she joined the Leibniz Institute of Polymer Research and is now working there in the Department of Polymer Interfaces. She led and leads fundamental and application-oriented projects on surface modification of polymers, or by using polymers including various physical-chemical characterization methods with a focus on topography and roughness wetting and Zeta potential. So in terms of agenda, we will start with our speaker's presentation, and then we'll go on to a presentation from Daniel Schultz of Data Physics Instruments before the Q&A session at the end of the event. A quick note on questions, please type these into the chat box and they will be marked for the Q&A sessions. We are planning to go for around 60 minutes in total today. However, if we do overrun, we apologize in advance. We have a quick GDPR announcement. There will be a few brochures and application papers from Data Physics. And if you download any of them, someone from Data Physics might be in touch to provide further support. We will be offering attendance certificates for live attendees today. The link will be shared later on in the event. And a quick reminder of our website, which is surfaceventures.org. It features videos from our previous talks and information regarding upcoming webinars and information about the Surface Ventures team. So we're going to have a quick poll which should appear on your screen very soon. We'd like to learn a little bit about you. So the question today is, what is your current position? That's great. It seems we have quite a good mix of different professions. So on that note, I'd like to hand over to our first speaker, Dr. Astrid, over to you.
Okay. Good afternoon, ladies and gentlemen. Thank you, Tahid, for the nice introduction, and thank you for having me here. Just maybe you can see more of me. Thank you for having me here, and thanks to everybody for joining today to hear my talk. Today, I'm going to talk about how we at Leibniz Institute for Polymer Research in Dresden use Zeta potential to understand structure property relations in polymer materials. First, I'm going to tell you some facts about my institute. Then I'm going to talk about what is the Zeta potential, why do we measure it, how do we measure it, and how do we interpret the measurements. I'm going to talk a little bit about the history of Zeta potential measurements at our institutes and come to the main part of my talk, the examples from our current research. In the end, I will talk shortly about practical problems and give a short summary. So the Leibniz Institute of Polymer Research is one of the big German polymer research institutes. It's situated in the beautiful city of Dresden. Maybe you've heard about it already. Here I show some nice historic buildings of our city and the already slightly historic main building of our institute from the 1950s. The institute was founded already in 1948 as a textile research institute. At that time, a lot of synthetic fibers were developed, and there was a big interest to find out how they can be improved, how they can be made closer to natural materials. With the time, the focus moved from synthetic fibers only to polymers in general. That's why our institute was renamed Institute of Polymer Technology in 1984. And after the German reunification in 1992, it was refounded as Institut für Polymerforschung Dresden, so that's the German name, so Institute of Polymer Research. It is member of the Leibniz Research Association. That means it's a research institution of supra-regional importance focused on application-oriented fundamental research. In 2011, we were co-founders of the Dresden Concept Network with the Dresden University and other Dresden research institutes. Our institute has about 500 co-workers, 50% of them are scientists from various fields of work, physicists, chemists, engineers, and so on. We have a lot of students and guest scientists, but of course also lab staff, technicians, administration, and so on. We have a regular budget from Saxon and German governments of nearly 30 million euros, but we also apply for a lot of funding from third-party funds for our research project. So it's again 14 million euros we get from third-party funds. The Leibniz Institute of Polymer Research does interdisciplinary holistic polymer research. What's that? So we do research from fundamentals to applications, from soft and adaptive functional materials to process-controlled structural materials. And we start from the polymer design on the molecular scales to finally application-oriented components and systems. Our goal is to produce or to develop sustainable materials for future technologies, as for instance, organic electronics, smart systems, energy, environmental and coating technologies, lightweight solutions, medical applications, and many, many more. Our institute is subdivided in 5 smaller institutes that deal with parts of this research strategies and which are situated at different positions of the innovation chain. So we have the Institute of Macromolecular Chemistry that deals with the design and synthesis of polymers on the molecular scale. We have a theory institute that does polymer theory and modeling, an institute that deals with biomaterials and bioengineering for medical applications. We have one institute, the Institute of Polymer Materials, that is very application-oriented. They deal with materials technology, processing, and testing. And I come from the Institute of Physical Chemistry and Polymer Physics. So we are dealing, as the name says already, with physical chemistry and physics of polymer materials. Polymers are very, very interesting materials. Many of you, or most of you, probably know the simple mass polymers, the unpolar polymers like polyethylene, polypropylene, or also the fluorinated polymers as Teflon. But it is possible to apply many different functional groups to polymers to change their properties, to make them hydrophilic, hydrophobic, reactive, and whatever. And our goal is to understand and control the interfacial phenomena in such polymeric systems and the design of polymers with tailored surface properties. On one hand, by chemically binding functional groups to the polymeric molecules. On the other hand, also by surface treatments, for instance, by plasma irradiation, chemical bonding, and so on. And to understand all these things, we do a very sophisticated surface characterization by many different methods. Here I show only a few examples. And today I'm going to talk about one of them, mostly the electrokinetics measurements That means the measurement of the Zeta potential with the goal to identify the surface functionalities. So what is the Zeta potential and why do we measure it? If you have a look at Wikipedia, you see Zeta potential is mostly known as a measure for the stability of colloidal dispersions. Probably you have heard about this too, but it's much more than this. The Zeta potential is a defined property of solid surfaces. It is actually the electrical potential of a solid surface, not only of small particles, but also extended surfaces in contact with a solution. Usually in aqueous solutions, but it is theoretically also defined for other polar solutions, but in practice, that's a little bit difficult. The Zeta potential can be measured for various geometry by different kinds of electrokinetic measurements. And it gives us information on all kinds of charge formation processes at the solid surface, mostly in water, but not only. So on this slide, I summarized some of these charge formation processes. So there are examples like dissociation of functional surface groups, chemical reactions, the adsorption of water molecules, but also dissociated water means hydroxide ions or hydronium ions, the adsorption of, of other ions from dissolved salts from the solution, complex formation, the adsorption of polymers, polyelectrolytes, surfactants, cells, and so on. And these charge formation processes are very important for many, many applications, as for instance, colloidal stability, chemical reactions, gluing, coating, painting, membranes and filters, but also the filler matrix interaction in composites, the sizing of fibers and textiles, oil recovery, energy storage, and many, many more. To understand the Zeta potential, we need to know a little bit more about the electrical double layer. There are a lot of theories about the electrical double layer. I only want to give you a very short impression. So if you put a solid surface, a particle, or an extended surface into a solution, into an aqueous solutions, there are ions in the solution, even if it's only water, because water auto-dissociates. And these ions adsorb to the solid surface and form an immobile layer on the surface. This may also include larger molecules like polymers or surfactants. And you have this strongly adsorbed ion or molecule layer on the surface of this, on the solid surface. It's called the immobile ion layer. And you have more ions around in the solution. They can move freely, and that's why they are called the mobile ion layer. And if you move the solution with respect to the solid surface, you get a slipping plane or shear plane between this immobile and the mobile ion layer. And the Zeta potential is the electrical potential exactly at this slipping plane between the immobile and the mobile layer. It is not the surface charge itself. The surface charge cannot be accessed to this adsorbed ion layer, but it's kind of measure of the surface charge. So how do we measure the Zeta potential? For this purpose, we use the so-called electrokinetic measurements. Electrokinetics means we have a motion of a liquid relative to a charged solid surface. Then we get the so-called electrokinetic effects. That means we have a transformation of electrical energy into mechanical motion, or vice versa, depends on the experimental setup. We have two basic setups depending on what we want to measure. Either we have particles that are dispersed in a liquid, or we have a flow through thin charged capillaries. I'm sorry, I have a little cold, so I have to cough sometimes. Yeah, and depending on the experimental setup, we either apply a voltage or an electric field to create a motion of the particles or of the liquid through the capillaries, and measure then the velocity, the vibration of the particles, or the volume flow. These are methods called electrophoresis, electroacoustics, electroosmosis. On the other hand, we also can apply a mechanical force, as for instance gravity, pressure, or ultrasound, and create the motion in this way. And then we can measure an electrical signal, an electrical potential or current. This is done in methods like sedimentation potential, electroacoustics, the other way around, or streaming potential and streaming current. On this slide, the most important electrokinetic methods are summarized. I don't want to explain everything in detail. I just want to tell you for different sample geometries, like for instance fibers, powders, plates, or foils, or particle dispersion suspensions, there is a method that enables us to measure the Zeta potential, and there is an equation that allows us to derive the Zeta potential from measurable quantities. So when we have measured the Zeta potential, of course, we need to interpret them because the Zeta potential itself doesn't give too much information. So I come back to this scheme I showed you already. The Zeta potential measurements show the combined effect of all these charge formation processes. That's why it's very difficult to interpret a single Zeta potential measurement, but some processes can be studied separately if we do a pH-dependent Zeta potential measurement series, a concentration-dependent series, or time-dependent series. That's why we usually don't do single measurements, single point measurements, but always these measurement series. For instance, with a time-dependent measurement, we can see swelling of a surface. If we bring a swellable, hydrophilic surface in contact with a solution, it takes up water. And when the water content increases, then of course the potential difference between the solid and the surrounding water decreases. The absolute amount of the Zeta potential decreases, as can be seen in the graph shown here at the right-hand side. Of course, there are other effects that lead to a time-dependent change of the Zeta potential, like for instance, the dissolution of charged surface coatings or chemical reactions. So it's always necessary to know the system we are measuring to understand what we measure. What we mostly do are pH-dependent measurements. Here you can see typical Zeta potential, pH-dependent Zeta potential curves for different kinds of surface functionalities. An important parameter is here the so-called isoelectric point, the zero crossing of the Zeta potential. If the isoelectric point is very low, below pH 3 approximately, then we know we have acidic surface groups. If the isoelectric point is above pH 7 or 8, we have basic or alkaline groups on the surface, and if it's somewhere in between, we have either an amphoteric or an uncharged surface. A typical feature of Zeta potential curves of charged surfaces are the pronounced plateaus at low or high pH values. We don't see this for uncharged surfaces. Another possibility are concentration-dependent Zeta potential measurements. Here we see some typical curves for strongly adsorbing cationic species, for instance, multivalent cations or cationic surfactants or polymers. This is the red curve. These species lead to a charge reversal of a negatively charged surface. If we have strongly adsorbing anions, we see an enhancement of the negative charge. And if we have uncharged surfactants, for instance, or other strongly adsorbing species, we see a screening of the Zeta potential, a decrease of the absolute amount of the Zeta potential. Another thing that is important to know if we have a look at Zeta potential measurements is the extremely strong adsorption of hydroxide ions on all surfaces. In the top graph, you see a comparison of concentration-dependent measurements in potassium chloride and potassium hydroxide, and you see how increase of the hydroxide concentration increases the amount of the negative Zeta potential, while the chlorine ions don't have a big effect. And that is the reason that an intrinsically uncharged and unpolar polymer like Teflon does have a pronounced Zeta potential. Its isoelectric point is around pH 4 because of the very strong adsorption of the hydroxide ions above pH 4 that lead to a strong negative Zeta potential. Now I come to the Zeta potential measurements at our institute. At the IPF, we have a very, very long tradition of Zeta potential measurements. Already in the 1960s, when we were a pure fiber research institute, there were Zeta potential measurements done. They were connected to the name to Professor Hans-Jörg Jakobasch. Zeta potential measurements were one important means to study the surface properties of synthetic fibers and to find ways to make them more similar to natural fibers. That's why they were performed a lot. In the 1980s, when the focus moved to polymers in general, the guys at our institute developed a setup to measure the streaming potential of polymer plates and foils. You can see here these nice ancient laboratory setups used at that time. In 1985, our institute had a very interesting cooperation. Professor Jakobasch tried to develop the first commercial device for Zeta potential measurements, and because no factory or no company in the former GDR was able or willing to do this, he got the permission, which was very rare at that time, to cooperate with an Austrian company, with Anton Paar, and together they developed the first commercial device for streaming potential measurements, the electrokinetic analyzer. This was for many years the single commercial device for that purpose. And it was used very, very much in our institute. Our workshop also built several measuring cells for special applications, for powders, fibers, but also for contact lenses, for instance. 10 years later, another device was developed at our institute. This is for very sophisticated fundamental research, but it also requires very smooth and homogeneous samples for very exact measurements. And 5 years ago, we started a cooperation with data physics instruments and supported them in the development of their new Zeta potential analyzers, ZPA, that will be presented afterwards in more detail by data physics. So IPF supported them with some fundamental research and with test measurements of the device. So now we're in the very nice position that we have a number of different devices for Zeta potential measurements of different surfaces, starting from molecules, complexes, and micelles. Well, in this case, this is not exactly the Zeta potential what we measure, because these things don't have a defined surface or a shear plane between the molecule and the solution. But anyway, we can study their surface potential and compare different molecules, for instance. Yeah, this is mostly done by the particle charge detector. For particles in solutions, we use mostly electrophoresis. Probably some of you know the Zeta sizer from Malvern. A method that is not so familiar is the DT 1200 used for electroacoustics measurements. Here the particles do not move like an electrophoresis, but are moved by ultrasound, and we measure an alternating current resulting from the motion. And this method allows us to measure the zeta potential of larger particles than with electrophoresis, and especially for particles in concentrated suspensions and emulsions up to 50 weight%. But most of our measurements we do with the streaming potential and streaming current method. We have now the current device of Anton Paar, the Surpass 3. We have the device from our house and also the prototype of the new data physics instrument. So let's finally come to the main part of the talk, the examples from the current research. Okay. Of course, we also deal with colloidal stability. Here you can see at the bottom the zeta potential, at the top the hydrodynamic diameter of different iron oxide nanoparticles, and for comparison of iron powder, these are the blue dots. The background of this research is the dispersion of these particles for use as fillers in polymer nanocomposites. For this, both the dispersion, the dispersibility, and the filler matrix interaction are of big importance. And you can see here very nicely for the oxide shown by the red dots, we have a low zeta potential at low pH values and an increasing negative zeta potential if the pH value increases. That's why these particles are well dispersed above pH 5, and they agglomerate at lower pH values when the zeta potential is low. For the particles shown by the black spots, it's quite opposite. They are well dispersed at low pH values and agglomerate at high pH values. So for practical applications, we have to select the appropriate pH range for our application. For the iron powder, it was a bit more difficult. As you can see here, neither the zeta potential nor the hydrodynamic diameters are well defined. The problem was that we had magnetic interactions between the particles during the measurement that really disturbed the measurement. Another kind of particles we are using in our institutes are carbon nanotubes. We use different carbon nanotubes prepared in different ways and with different functional groups. And in this case, they were intended for use in concrete, in cement applications for lightweight building components. And yes, what we did at the left hand, you see the zeta potential of different carbon nanotubes prepared in different ways, and you can see due to the different surface functionalities, they have very different behavior, from rather acidic, the red curve, or amphoteric more, to rather alkaline, the black and blue curve. And for comparison, this was done by electrophoresis, and for comparison, we also measured the zeta potential of different ingredients of the cement in the original concentrations, and for this we use the electroacoustics measurement. Another field of our work is the functional coating of nanoparticles. So we use different nanoparticles, cover them with polymers, in this case a so-called polymer brush. That means the polymer chains are attached at one end to the particle surface and extend freely into the solution. We normally start with a particle, in this case a small silica nanoparticle. We apply an aminosilane to create amino groups to the surface. Then a bromo initiator is attached to these amino groups. And in the end, from these bromine groups, a polymerization reaction starts that results in these polymer chains, this so-called polymer brush. To make sure that the surface modification is successful, we have to verify each single step of this procedure. And for this purpose, Zeta potential measurements are the method of choice. So we start with the silica particles. These are the black spots here. Then the silane has alkaline properties, silane groups. That's why this modification step moves the isoelectric points to values above that. The bromo initiator then brings the isoelectric point back to pH 4, and finally the alkaline polyelectrolyte brush has again an isoelectric point at pH 9 to 10. And so we have to check after each step if the typical isoelectric point is reached in the Zeta potential measurements. This is the method for us to check if the modification was successful. Another example of polymer or polyelectrolyte brushes are responsive coatings. In this case, we compare 3 different kinds of brushes: an acidic brush, polyacrylic acid brush that has the property that it is collapsed at low pH value and swells at high pH value. The poly-2-vinyl pyridine brush is an alkaline brush. It has the opposite behavior. It's swollen at low pH and collapsed at high pH value. And if we mix these 2 components, we get a so-called mixed brush. And this mixed brush changes its properties from those of poly-2-vinyl pyridine at low pH values when this P2VP is swollen to polyacrylic acid at high pH value when the polyacrylic acid is swollen. And you can see this very nicely in the Zeta potential curves shown on top of the left graph. You can also see it in contact angle measurements, and you see the swelling in brush height measurements. But the Zeta potential shows very nicely the switching from the P2VP properties to the PAA properties for the mixed brush. We also use thermoresponsive brushes that are swollen, for instance, in this case, at low temperatures and are collapsed at higher temperatures. We don't see a pronounced change of the isoelectric point in this case in the Zeta potential, but we see a decrease of the Zeta potential at low temperature as a result of the swelling. As I explained, if you have more water in the brush, then the potential difference between the brush and the surrounding solutions becomes smaller. This is a slightly older example. This was a work we did for microelectronic industry for Infineon. The guys had very big problems in the photolithography due to capillary forces during the drying after the development of the photoresist structures. Sometimes the photoresist structures collapsed during the drying. Sometimes remainders of the photoresist remained on the wafers and caused defects. And it was clear that this was an effect of capillary forces, and that's why we tried to find a method to reduce the capillary forces. And the idea was to rinse the photoresist structures with cationic surfactants after the development. And to find out how this works, we again applied various methods. We measured the surface tension of the solution. This is the top image. We measured the adsorbed amount of surfactant on the photoresist. And we also measured the Zeta potential and the contact angle of the photoresist after the deposition of the surfactant. And you can see that the Zeta potential is the most sensitive method to detect the deposition of the adsorption of the cationic surfactant. Already at very low concentration, we see a charge reversal in a concentration range when only single surfactant molecules are adsorbed on the surface. And finally, we found out that at a concentration of about 10% of the critical micelle concentration, we have a maximum of the contact angle, and this helped us to reduce the capillary forces and also prevented the defects. Another example also for microelectronics industries, this was at the very end of the production line, the housing of the microchips. There were problems that the PDMS housings did not attach properly to the chips, and that's why we tried to improve the adhesion of PDMS, the polydimethylsiloxane, on metal surfaces. The method of choice was a plasma treatment. This also helped to reduce the contact angle and to improve the adhesion. But the problem with plasma treatment is that it's not very stable, so the surfaces recover with time. But what you can see in the Zeta potential measurements at the left-hand side, if we use oxygen plasma, we create acidic groups. We get an isoelectric point at pH 2.5. If we use ammonium plasma, we get alkaline ammonium groups and an isoelectric point at pH 5.5 approximately. But to overcome the problem with the recovery of the surface, we added an additional step. We adsorbed polyelectrolytes on these plasma-treated surfaces. And here again, you can see the effect of different polyelectrolytes, the polyacid that leads to a lower isoelectric point, an alkaline polyelectrolyte that leads to a higher isoelectric point, and the contact angle measurement at the right side show that with the adsorption of the polyelectrolytes, the effect on the contact angle and on the adhesion behavior was much longer stable than only after plasma treatment. Another application is the sizing of glass fibers. In our institute, glass fibers are often used as fillers or as reinforcement for polymeric composites. And to improve the filler matrix interaction, the fibers are sized. A usual method is to apply a mixture of a silane and a surfactant. In this case, the aminosilane amio and the cationic surfactant aquat S50. To do this in an economic way, it is important to study how this adsorption takes place, especially if you have a competitive adsorption of the two species. And in the image in the center, you can see how the Zeta potential changes if only the surfactant or only the aminosilane are adsorbed, and if they are adsorbed one after the other. And in the pH-dependent measurement at the right-hand side, you see that the glass fiber that has usually a very low isoelectric point due to its hydroxyl groups on the surface. And if we add the aminosilane, the isoelectric point shifts, so it has more alkaline behavior. And if we add both the aminosilane and the surfactant, then we get an even higher isoelectric point, and this can ensure better filler matrix interactions with the polymer. Now I come to a project I dealt with in the very last years. We studied together with a group from Technical University Dresden. We studied fiber reinforced concretes or cement materials. So you probably know that cement is usually very brittle. Normally it is strengthened by iron rods or something like this, but for lightweight applications it's also possible to add about 2% of short polymeric fibers. Sorry, they are able to bridge the gaps if there are small cracks in the concrete and strengthen the concrete. For this purpose, we need a very well-balanced interaction between the fibers and the concrete. If the adhesion between fibers and concrete is too weak, then the fiber is pulled out and does not have much effect. If the adhesion is too strong, the fiber ruptures and doesn't help very much too. But if we have a perfect adhesion, then the fiber is able to bridge the gaps, and we get many small cracks in the concrete instead of one final failure. We again tried to do this by adsorption of polyelectrolytes, by acidic and alkaline polyelectrolytes, but also by chemical bonding of aldehydes. And we studied many properties of these fibers, but especially the contact angle in water that is shown at the left side and the Zeta potential shown at the right side. And again, you see how the adsorption of the polyelectrolytes changes the Zeta potential and the isoelectric point of the fibers. And from these two measurements, we created a so-called property map of the modified fibers. You can see it in the middle. So here, for each type of fibers, we have a point symbolizing on one hand, the hydrophilicity or hydrophobicity of the fibers, and on the other hand, the acidic or basic behavior. And our colleagues at the Technical University took these fibers, put them into concrete and pulled them out and looked how is the interaction with the concrete. And we found out that after all the polyelectrolyte adsorptions, the interaction was still very strong. So we use polyvinyl alcohol fibers, which are polar and interact naturally very strongly with the concrete. And after the adsorption of the polyelectrolyte, the interaction was nearly the same or even stronger, and only with the aldehyde butanol we reached a weaker fiber matrix interaction. In this case, it was a bit too weak, but we later did other studies to control this effect a little bit better. We wondered a little bit why the polyelectrolytes did not affect the interaction very much, but then we put the fibers in diluted pore solution. Pore solution is the liquid you get if you filter fresh cement. So it's a solution that contains very many ions of different kinds. And if you put the fibers into this diluted pore solutions, you see that no matter at which Zeta potential the fibers have at the start, already in 1% pore solution, the surface charge is the same for all fibers. So probably that's the reason why this effect was not very big. There are a lot more applications for Zeta potentials, for instance, in the chemical industry, pharmaceutical industry, cosmetics, and so on. One application that is dealt with in another department of our institute, the Department of Functional Colloidal Materials, is the water purification and wastewater treatment. Here, the Zeta potential measurements are very interesting for the interaction with membranes, for flocculation, adsorption, and so on. Zeta potential is also very, very interesting for textile industry, paper and printing industry, glues and coatings to study, for instance, the stability of dispersions, adhesion, and so on. Our colleagues at the Institute of Biofunctional Polymer Materials do a lot of Zeta potential measurements for medical application to control the surface property of, for instance, prosthesis implants, to study dialysis or tissue engineering, and also cell growth and fouling. And as I told you already, for composite materials, for the filler matrix interactions, it's also very interesting. Now let's come to my last point, a few practical problems of Zeta potential measurements. There is still a debate if the Zeta potential is really a physical property of a solid surface, because sometimes the Zeta potential is measured for similar surfaces and you get different values. One reason for this might be the morphology or roughness of the surface. So in this, in the left example, we studied PVDF polymer surfaces with different roughness, and you see that the absolute amount of the Zeta potential is smaller if the surface is a little bit rougher. On the right-hand side, we did a study with polystyrene foil that in which we applied some scratches or trenches, and here you can also see that the Zeta potential, that the apparent measured Zeta potential values become smaller if you have these scratches in the surface, and it also depends on the direction of the scratches. But if you have a look at the schemes at the bottom, you maybe can imagine the reason for that. So according to theory, we have a defined shear plane on a very smooth and flat surface, and the shear plane is always at the same distance to the surface. But if we have a rough surface, of course, the liquid flow or the shear plane is not always at the same distance to the surface, and you may also have entrapped air in some voids, and that's why not all of the surface is accessible to the Zeta potential, and that's why the absolute value becomes lower. If you measure the Zeta potential of fiber or powder packages by streaming potential measurements, as symbolized by the image at the top right, you also see an effect either of the size of the particle or of the weight you put into the measuring cell. It means the number of particles. And to study this, we measured the Zeta potential of basalt spheres of different size and of different weight or number of particles. And we measured the liquid flow through this particle package. This is the liquid flow is shown as numbers beside the left image. And you see if the particles become bigger and the flow becomes higher, then the absolute amount of the Zeta potential becomes smaller. You can also see this in the right image, where the plateau value of the Zeta potential is drawn versus the liquid flow. The reason for this is if the capillaries between the particles become bigger, then again less of the particle surface is accessible to the measurement, and that's why the Zeta potential becomes smaller. So as a rule of thumb, we try to use for measurements on fibers or powder packages, we try to use always the same liquid flow if we want to compare different measurements. There are a lot of other possible error sources. For instance, in electrophoresis, if the particles are too big, if they sediment or agglomerate, then we get wrong values. For streaming potential or current measurements, errors may arise from incorrect attachment of the samples, or a deformation or swelling, or if the fiber or powder plugs are not prepared properly and you have holes, then you also may measure wrong values. Another problem are electrically conductive paths in the measuring cell. If you measure with electrically conductive materials, that's always tricky. And a very big influence is the dissolution of carbon dioxide from ambient air. That's why we always rinse our measuring solution with nitrogen. So if the carbon dioxide is dissolved, you get a lower pH value than you expected. You also have to take care that your sample does not contain soluble components that are dissolved during the measurement, or sometimes there may also be degradation of the sample at high or low pH value. And you have to take into account that Zeta potential measurements are very, very sensitive to contamination, both of the surface you measure and of your measuring solution. So you have to work very carefully. So finally, we come to the end. I thank everybody who joined me until now. I come to the summary. So the Zeta potential is the electrical potential at the shear plane or slipping plane between a solid and a liquid. If the liquid is in motion relative to the solid surface, it gives us information on surface functionalities, on dissociation, on absorption and swelling. These effects can partly be separated by pH, concentration, and time-dependent measurements. The Zeta potential can be measured by different methods depending on the geometry and size of the solid surface. So for instance, particle charge detector, electrophoresis, electroacoustic, streaming potential, and streaming currents. And Zeta potential measurements may be applied, for instance, for understanding of adsorption processes and interactions, the verification of surface modification, and the adsorption of polymers and surfactants, and the study of responsive behavior in aqueous environments. Zeta potential measurements are sensitive to contaminations, roughness, capillary geometry, and sometimes the surface conductivity has to be considered, but this is a very tricky topic that was beyond the scope of my talk today. So this is the end. I thank you very much for your attention, and of course I thank my colleagues at IPF, Dr. Bellman, who did a lot of work on Zeta potential measurement before she retired a few years ago. And many, many thanks to my lab technician, Anja Kaspari, who has many years of experience with Zeta potential measurements, who is known to some of the audience, as I have seen. And of course, I thank the whole team at IPF. And again, I thank also Data Physics and Surface Ventures for inviting me to give this talk today. Thank you very much.
Thank you very much, Dr. Astrid. Really insightful talk. At this point, we'd like to hand over to our partner at Data Physics Instruments, give a short talk, and then we'll come back for questions for Dr. Astrid. So I'll hand over to Daniel at the moment.
Okay, then. Hello, everyone. Thanks, Ms. Drechsler, for this interesting talk about basically everything that involves Zeta potential measurement. So why we do it, where we can do it, what all the applications are. And as she mentioned, the Leibniz Institute has, in cooperation with us, basically developed a Zeta potential device using an oscillating streaming method. So I'm here to talk a little bit about that, just a brief overview basically of how that works, what our device makes special basically. Okay, so first of everything, just a short introduction in who is Data Physics. So we are a small company in the south of Germany, close to Stuttgart, and we are developing since 25 years instruments for surface science applications. So that started with contact angle goniometers and tensiometers, so basically to test wettability, surface tension, adhesion properties, things like that. In the meantime, we also have a spinning drop tensiometer and a stability analyzers for the emulsions and dispersions. And the newest device in our product line is the Zeta potential measurement. So a short scheme basically of how the device works, how it's set up. So you have the gray box, basically the device itself, where all the electronics are inside, and the motor to drive a piston is inside. The main part of the instrument is basically up in front, so in the image on the left side. So you have in green the sample cell. There are different sample cells for different kind of surfaces. So the device itself is meant to measure the Zeta potential and streaming potential for macroscopic surfaces, so for actual plates, for fiber bundles, for granulars, stuff like that. So not for particles in solution, but really for really solid materials. So there are different sample cells to be mounted into the device. And the measurement electrodes in orange are just on top and below of the sample cell, so that the liquid is flowing through the electrodes, through the cell, through the next electrode, and back and forth, basically. You have in blue the liquid reservoir, so the electrolyte solution that is streaming through the cell. On top of the instrument, basically, you have a conductivity sensor and a pH sensor to always measure these values at the start of each measurement. And you have the option to have an automated liquid dosing system so that you can set up a program and vary the pH value of your measurement setup, basically live in the measurement. For sample preparation, for mixing everything, for cleaning, there is a liquid bypass that bypasses the cell and the sample, so that's that you can mix easily and get the system cleaned easily. The same for the outlet. So the system is very smooth. There are no hard edges, so you can clean it easily. And also there will be a heating system so that you can also make your measurements at temperature and not just at ambient room temperature as well. So that's the basic setup basically of the instrument. And as said, with the stepper motor, you move the electrolyte solution through your sample cell, through your sample, and in an oscillatory way, basically, measure the streaming potential then through the sample and up and down. And to you on the right side, you see the instrument, how it actually looks. And to make the measurements, you have to make a measurement at alternating pressures as well. So as said, with these pistons that we have in there, on top of the piston, there is a pressure sensor mounted. So you can define a range of pressures that you want to use, and the system with the software will automatically make a sinusoidal pressure wave, basically, and pump the liquid through the sample and suck back and do different cycles, as many as you like, basically, just to do your measurement. So with that, even during one cycle, you get a lot of different pressure differences where you can, which you can use then to get your streaming potential. And that also makes it very easy to get more statistical relevant values. So basically just not doing just one cycle, you make several cycles and just increase the data that you get from the system. You get many different pressure values, you get a lot of different results, you get the statistics, just makes it very fast, very easy to get a reliable result with this system. So from the setup, basically, so the software looks like that. On the top, I'm not sure if you really can see it, but on the top you have the different measurement points, the streaming for setup potential at different pH values. For one of these points, you have the curve on the lower side there, where you see the oscillation. So one of the graphs is the pressure graph, and the other one is the Zeta potential, the streaming potential. And as we circulate through the sample, so going back and forth, oscillating through it, you will see also if there is any differences in the direction of the stream. So if you have an ideal surface, just like a very ideal silicon wafer or something, you would expect that it doesn't matter which direction you stream it through. And in reality, we rarely have ideal surfaces. So with this system, as you go back and forth, you will see if there is a difference, and if there is a difference, what kind, how it shows in your measurement profile, basically. And you see that as an example in the red circles there. So the green one is actually the pressure that's oscillating through the system. The streaming potential is the orange graph. So basically the graph going down is one direction, the graph going up is the other direction. And you see some differences in this example here. And well, so that gives you one more thing to study, and one more idea of how ideal your preparation actually is. So as said, ideally you want to have it as similar as possible. So going to the next slide here. So the ZB820 is made for solid substrates. I mentioned that. So for plates, fibers, membranes, granulars, powders, and allows you to measure the surface charge depending on the pH value to get the isoelectric point of the sample. And there are different sample cells depending on the materials that you're using. So there is a gap measurement cell that is especially for solid plates, for membranes. And there is another cell that allows you to measure with fiber bundles, with powders, nonwovens, things like that. And there might be other cells for different sample geometries coming up as well in the future. From the measurement principle, I said it's an oscillating streaming method. So we go back and forth through the sample. Therefore, we get during even one measurement cycle a lot of different pressure differences that we can use for the calculation. You get a lot of just data points, basically, to make it a really accurate measurement with the excellent statistics that you get out of there. And with the automated dosing system that we also have as an option, you can just program your pH values, basically program how many steps you want to do to get an isoelectric point measurement, and completely automatically basically define how many measurements, how many cycles, which pH values, how many steps, and really automate the complete system, the complete setup, so that you get your result at the end basically just with a very easy preparation then. Again, this will be possible to do at different temperatures, and handling of the device with the design, with the open design that it has, is very easy to get your sample cell in, to clean it afterwards efficiently. It's well designed and easy to use in that term. So that's already the end of my short ZBA introduction there. And if you have any questions, please let us know. Send us an email, ask questions in the chat. We will be happy to assist you in any way there. I think there was one question in the chat I saw about the sample size. So typically, for our system, that's 1 by 2 centimeters. And I think that's the typical thing in lab scale instrumentation. I'm not sure if there is anything where you can make it on a bigger scale. At least I'm not aware of. Okay, thanks.
Thank you so much, Daniel. So we'll go back to Dr. Astrid and we'll take some questions. There's a few questions in the chat box. If you have any other further questions, please do put them in the chat box. The question should appear on our screen very soon. The first question is, how is the implementation and approach of machine learning and new technologies in polymer research as a whole?
I think this question goes to me. We are currently in a stage of introducing such stuff into our research, but well, actually, most of our research is more fundamental related, and that's why we do a lot of measurements manually, and it's very difficult to implement machine learning and such stuff. But we are currently preparing a new part of our institute that tries to do that.
Brilliant. So we'll move on to the next question. Is there any commercial Zeta potential measuring device for large-scale polymer surfaces?
Yeah, well, I know that the device of Anton Paar has a special cell for large-scale surfaces, not really large-scale, but it's a so-called clamping cell that takes a larger sample at one side and puts uses the cell material as the other side, but in this case you always get a mixed Zeta potential of the large sample and the cell wall, and it's really difficult to interpret this. Yeah, the problem is that you need this very thin measuring slit, and it's really difficult to implement it practically for large samples, I guess.
Makes sense. We'll move on to the next question. The measurement of a surface potential is easier, faster using a device from Anton Paar or a device from data physics?
That's a good question. I should ask this my lab assistants, because she did the measurement, but she just enjoys her holidays. That's why she's not here today. The main time-consuming thing in Zeta potential measurement is the equilibrium. So I think that the data physics device is a bit faster in mixing the solution due to this oscillatory movement. So if you add some potassium hydroxide or some acid to the solution to change the setup, to change the pH value, the mixing is a bit faster with with the data physics device, but in fact you have to wait for equilibrium in any case, and that's the limiting factor.
Sure, great answer. I think we have one final question. Can we measure Zeta potential of polymer films in alcohols or organic solvents?
Yeah, we've been asked this already several times. Basically, it is possible, but if you want to have the real Zeta potential in an organic solvent, you need to get it absolutely water-free, and you won't get it if you work in normal lab surroundings. You always have humidity from the air, you always have water that goes into the solvent, and it goes to the surface, and then you measure the Zeta potential of a surface with adsorbed water.
Right. And we have another question. How can we have stable solution of nanoparticles in water? How do you test it? By measuring the Zeta potential.
Yeah, that's very old knowledge. If the nanoparticles are charged, that means if their Zeta potential is higher, or the absolute amount of the Zeta potential is higher than about 30 microvolts, then the solution or dispersion is usually stable. And if they are rather uncharged, because we are in a pH range when the Zeta potential is rather low, then usually the particles agglomerate. But of course, it depends. The particles can also be stabilized by polymers or swelling stuff or something. So there are different ways. It's difficult to get a simple answer.
Perfect. I believe that's all the questions. So on that note, I would like to thank the audience for the questions. I'd also like to thank Dr. Astrid Drechsler for such an engaging talk. Thank you for sharing. We really appreciate it. Pardon me. Also like to thank our partner, Data Physics Instruments, for supporting this webinar. As a reminder, please do visit our website where you can access this talk and previous other talks. We will aim to organize the next webinar in September, so the 29th of September. So please do stay tuned on our website, emails, and LinkedIn for further updates. We also have a fortnightly newsletter, Modern Surface. By signing up to our mailing list, you can receive this. And our first issue will resume after our August break, so it'll be in 9th of September. We also like to take this time to ask for your support in advertising these lectures to your contacts. So on that note, thank you very much for attending, and we hope to see you again soon. Enjoy the rest of the day and enjoy your summer breaks. Thank you very much.
Thank you.
Thanks. Bye.